All right, welcome back to the deep dive. Today we're diving into something pretty fundamental, to philosophy and mathematics, logicism.
Yeah, absolutely.
So for our fellow, philosophers out there, we're going to be talking about can we ground all of mathematics in logic?
Right.
And specifically, we're going to be looking at arithmetic and real analysis today.
Okay. Yeah.
And for our sources. The main source we're going to be looking at is the Stanford Encyclopedia of Philosophy's entry on logicism and neologicism.
Great.
So just to kind of give a brief overview, what is logicism? What is the kind of core idea here?
Well, I think a good way to put it is it's the idea that all of mathematics, or maybe just arithmetic and real analysis, can be reduced to logic.
Okay.
To logic.
Yeah.
So the idea is that mathematics is just logic in a deep way. That's the kind of program.
Right. Yeah.
And there are two kind of main versions of this: a strong and a weak version.
The strong version is that all mathematical truths are just logical truths.
Yeah.
Just maybe kind of hidden or expressed in a different way.
Yeah.
And then the weak version is that all mathematical theorems are provable from just logic.
Mm-hmm.
So you might think that that's maybe less audacious, but if you could show that, I mean, that's still pretty huge.
Yeah, absolutely. And in fact, both of those versions rely on two big tenets.
Okay.
The first is that the subject matter of arithmetic and real analysis are logical objects.
Yeah.
The second is that the first principles of these branches can be defined in logic and derived, from just logic.
So the idea is that you can take something like the concept of a number and you can define that using just logic.
Right.
And then from that definition you can get all of arithmetic.
Exactly.
Okay. Now this brings to mind Kant and the analytic synthetic distinction. Right?
Absolutely. Yeah.
Because logic is the classic example of something that's analytic, right? It's true in virtue of the meanings of the terms involved or the relations between the concepts that are being used in a proposition,
right?
And so the Logicist project is really trying to show that math is like that too, that it's analytic in that way.
Yeah, that's right, and that would mean that mathematical knowledge is a priori in the same way that logical knowledge is.
Yeah.
You don't need to appeal to experience to justify a mathematical claim if it's analytic, if it's reducible to logic.
Yeah, it's just true in virtue of the meanings of the terms and the logical relations between them.
That's right.
Okay, so that's the overview. That's the big picture. But as everyone knows, the history of philosophy is rarely that straightforward. And logicism has had kind of a complicated history. So we're going to kind of go through some of the big figures and the twists and turns in the story. So some of the big figures in logicism, well, we've already mentioned Kant, but of course Frege, right?
Right, Frege, Russell, yeah.
And then there have been setbacks too. Famously Gödel's incompleteness theorems.
Yeah.
And the rise of set theory have kind of posed challenges to logicism. But then more recently, there's been a revival in the form of what's called neologicism. So we'll kind of go through all of that and see how logicism has changed and evolved over time.
Right. One of the things that's central to the neologicist revival is this really interesting idea called abstraction principles.
Okay.
And they work by securing the existence of mathematical objects, so things like numbers, based on logical relations.
Okay. So give an example. How would this work?
So take, for example, the direction of a line. So if two lines have the same direction if and only if they're parallel. So an abstraction principle will take that logical relation, the relation of being parallel, and then it will say there's a kind of object, a new kind of object called the direction of a line.
Okay.
And that's sort of derived from the logical relation of being parallel.
So it's like taking that relation of parallelism and then reifying it.
Exactly. That's a great way to put it.
Okay. Turning it into an object.
Right.
Okay, I think I see.
Yeah.
Okay, so the history of logicism isn't this smooth progression. It's really this series of bold attempts and then challenges and then rethinking how to go about it. And really what's at stake here is can we ground the seemingly certain truths of mathematics in the bedrock of logic itself?
Right.
And that's the big question.
That's the big question, yeah.
Okay, so let's go back to Kant then.
Yeah.
I mean, he's really the starting point for a lot of these discussions.
Right.
So how did Kant think about math? What was his view of arithmetic and geometry?
Yeah, so Kant famously argued that both arithmetic and geometry are synthetic a priori.
Okay. Synthetic a priori.
Yeah, and just to unpack that a bit.
Yeah.
So something is synthetic if it provides us with new knowledge, if it tells us something that we couldn't have just gotten from analyzing the concepts involved.
Okay.
And it's a priori if it's independent of experience. So if it's accessible to us through pure reason.
Okay, so math is giving us new information. It's not just like analyzing concepts we already have.
Right, exactly.
But we don't need to go out and do experiments or anything like that. We can figure it out just by thinking.
That's right.
Okay.
Yeah.
And Kant had a famous example for this, right?
He did, yeah.
Yeah.
His go-to example was 7 + 5 = 12.
Okay. 7 + 5 = 12.
Yeah.
Okay, so walk us through how Kant thought about this example.
Yeah, so for Kant, the idea is that if you just think about the concept of 7 and the concept of 5, and you think about addition, putting those two together, you don't immediately get the concept of 12.
Right. It's not like 12 is already there somehow in the concept of 7 and 5.
Right. It's not like you're just analyzing 7 and 5 and addition and then, oh, look, there's 12.
Right. It's a genuine kind of new piece of knowledge.
Yeah, it's a discovery, right? It's a discovery that 7 + 5 = 12.
Right.
You're not just, unpacking concepts that you already had.
Right. Okay. And then what about the a priori bit? Why did Kant think that this was something that we can know just through pure reason?
Yeah, so for Kant, the a priori nature of arithmetic stemmed from what he called the pure form of our intuition of time.
Okay. Pure form of our intuition of time.
Yeah. So this is the idea that time, as we experience it, has this kind of structure to it.
Okay.
Right. It's an unbounded series of successive moments.
Okay.
And it's our grasp of that structure of time that allows us to count and to understand arithmetic.
Yeah.
So that's why arithmetic is a priori for Kant. It's grounded in this pure form of our intuition of time.
Okay.
And geometry, similarly, is grounded in the pure form of our intuition of space.
Okay, so space also has, for Kant, some a priori structure.
Right. Things like, straight lines, the fact that space is continuous, these kinds of things. For Kant, we're part of the pure form of our intuition of space.
Okay.
And that's what grounds our a priori knowledge of geometry.
Right. So geometry is not something we learn from experience. It's already built into how we think about space.
Exactly. Yeah.
Okay. But now the logicists are going to come along and they're going to say, wait a minute. We think at least arithmetic is analytic. Right. It's not synthetic. We can show that it's true just in virtue of the meanings of the terms and the logical relations between them.
Mm-hmm.
Okay, so before we get into Frege and how he tried to do that,
yeah,
there was one other figure that I think is worth mentioning here, and that's Dedekind.
Yes, Dedekind, absolutely.
Yeah. So how did Dedekind contribute to this logicist project?
Well, Dedekind really enabled or helped enable the culmination of this trend towards the arithmetization of real analysis.
Okay, arithmetization of real analysis.
Yeah.
So that's basically trying to ground calculus and things like that.
Yeah.
In it just arithmetic.
Right, exactly. And this is a trend that had already been sort of going on, even with Gauss, with Bolzano.
Okay.
It really came to a head with Cauchy and Weierstrass.
Okay.
But Dedekind was really kind of a key figure in bringing this to its culmination.
Okay. So he was basically saying, look, we don't need to appeal to geometry to understand calculus. We can do it all just with arithmetic.
That's right. And he was very explicit about this. In his book Stetigkeit und irrationale Zahlen, continuity and irrational numbers.
Okay.
He has this methodological maxim where he says we should try to avoid using geometric intuition when we're trying to give foundations for real analysis.
Okay.
That the foundation should be purely arithmetical, he says.
Okay. So
Yeah.
he's kind of rejecting Kant's, insistence on space as this fundamental intuition
Right.
for grounding math.
Yeah, he thinks we can do it all with just numbers.
Okay.
Yeah, and in another one of his works was in the Zone die Zacherwahlen. What are numbers and what should they be? He's very explicit about this.
Okay.
He says that the number concept is entirely independent of notions of space and time.
Okay.
That it's an immediate product of pure thought.
Okay.
Yeah.
All right. So he's already kind of going in a logicist direction.
That's right.
By saying that we don't need to appeal to these Kantian intuitions, that arithmetic is somehow fundamental and independent of those things.
Exactly.
Okay. So then along comes Frege.
Yeah.
And he really gives us the tools to start to really formulate this logicist project in a precise way.
Right.
So what did Frege do that was so important here?
Yeah, so Frege's big contribution was the development of a formal deductive system of logic.
Okay.
And this was really essential for logicism.
Okay. Why was that so essential?
Well, if you want to say that all of mathematics is reducible to logic, you need a rigorous way of expressing that.
Right. You need to be able to actually say what you mean by logic.
Exactly. You need a precise system of logic.
Right.
And that's what Frege gave us.
Okay.
Yeah.
So he gave us the language to even talk about logicism in a clear way.
Exactly. Yeah.
Okay. And then he actually tried to do it. He tried to actually carry out this logicist reduction.
Right. So in his work, Begriffsschrift, which is often translated as concept script, he really lays out this idea.
Okay.
He agrees with Dedekind on a lot of the methodological issues.
Okay.
And he aims to give a logicist treatment of arithmetic.
Okay.
So, for example, he distinguishes between truths which only require justification by reference to logic.
Okay.
And then truths which require some fact about the world.
Okay.
Some empirical fact.
Okay. So he's trying to say, like, there are some truths that we can just know through logic.
Right, exactly.
And then there are other truths that we have to go out and like look at the world and see.
That's right, yeah.
Okay.
And his aim was to show that arithmetic fell into the former category.
Okay.
That arithmetic truths are the kind of truths that don't require any empirical justification.
Okay. So how did he try to go about showing that?
Yeah. So I mean, one of the things that Frege did was he really developed this idea of analyticity.
Okay.
So we already mentioned Kant's idea of analyticity.
Yeah.
But Frege kind of took it a step further.
Okay.
So for Frege, the idea was that a judgment, so a kind of statement that we might make is analytic if it can be proved, from just general logical laws and definitions.
Okay.
Yeah.
So he's saying even if the concept isn't like explicitly contained in the subject, like Kant was saying,
Right.
if you could derive it from purely logical principles,
Yeah.
then it counts as analytic.
That's right. Yeah, that's a really nice way to put it.
Okay.
Yeah.
So he's got this more expansive notion of analyticity.
Exactly. Yeah.
Okay.
Yeah.
So let's go back to Kant's example then of 7 + 5 = 12. Right. So Kant said, look, the concept of 12 isn't contained in the concepts of 7, 5, and addition.
Right.
But Frege would say, well, actually, if you define things in the right way, you can get that result just from logic.
Right. Yeah. So Frege introduced this idea of the successor function.
Okay.
So the successor of 0 is 1, the successor of 1 is 2, and so on.
Right. So it's just like adding 1.
Right. Exactly. It's just adding 1.
Okay.
Yeah. And then he also gave recursive definitions for things like addition.
Okay. Like what's an example?
So, for example, he would say x plus 0 is equal to x.
Okay.
Right. And then he would also say x plus the successor of y is equal to the successor of x plus y.
Okay.
Yeah.
So using those definitions and his system of logic, he can actually derive 7 + 5 = 12.
That's right. Yeah. He can show that statement follows just from the definitions and the logical axioms.
Right. So for Frege, 7 + 5 = 12 really is analytic.
Yeah, it's analytic in his more expansive sense.
Right.
Exactly.
Because it can be derived from just these logical principles.
Mm-hmm.
Okay. Now another really important thing that Frege did was was to think about numbers as what he called higher level concepts.
Right.
So what did he mean by that?
Yeah, this is a really tricky but a really important idea.
Okay.
So Frege's idea was that a statement about a number isn't really about the number itself as an object.
Okay.
It's actually an assertion about a concept.
Okay.
So for example, if you say the number of apples in the basket is 2,
Okay.
what you're really saying is there are exactly 2 apples in the basket.
Right. Okay.
Right. So it's an assertion about the concept of apple in the basket.
Okay. So instead of talking about the number 2 as this thing,
Yeah.
we're talking about how many things fall under this concept of apple in the basket.
Exactly. That's a really nice way to put it.
Okay.
Yeah.
And he even had like a way of expressing that without using the number 2.
Yeah, he did. So if you want to say there are 2 apples in the basket, without using the number 2, you can say something like, well, there's an apple in the basket,
Good.
and there's another apple in the basket, and these 2 apples are not the same, and there are no other apples in the basket.
Okay. So you're just describing like the objects that fall under the concept.
Exactly.
Okay. And then the 2 is kind of like a shorthand for all of that.
Right. The 2 is just a way of picking out the numerosity of that concept.
Okay.
Yeah.
So he's kind of recarving our thoughts about numbers as thoughts about concepts.
Exactly.
Okay.
Yeah.
Now, to formalize this, he introduces some notation.
Right.
He uses a $ F or $ X FX to denote the number of Fs.
That's right.
So this is like a way of talking about the number of things that fall under a concept. Okay.
Yeah.
And so the statement $ X S equals 2 is basically just a second order logical statement, right?
That's right. Yeah. It's a statement about the existence of exactly 2 Fs.
Okay, so it's not really about the number 2 as an object.
Right.
It's about this concept and how many things fall under it.
That's right. It's about the numerosity of the concept.
Okay. All right, so this brings us to Hume's principle.
Right.
Which is a really important principle in the history of logicism, especially for the neologicists.
Yeah.
So what is Hume's principle? What does it say?
So Hume's principle, it's often just abbreviated HP.
Okay.
It says that the number of Fs is equal to the number of Gs if and only if there's a 1-to-1 correspondence between the Fs and the Gs. So what that means is if you can pair up the Fs and the Gs in a way that every F is paired with exactly 1 G and vice versa,
Okay.
then the number of Fs is equal to the number of Gs.
Okay.
Yeah.
So we have like 7 apples and 7 oranges. We can pair them up.
Exactly.
And that means that the number of apples is the same as the number of oranges.
That's right. Yeah.
Okay.
Yep.
Now why is this so important for logicism?
Well, the key thing is that the notion of a 1-to-1 correspondence can be defined purely in logical terms.
Okay.
Without appealing to numbers.
Right. You're just talking of relations between objects.
Right. You're just talking about, there exists a relation such that, for every F, there's exactly 1 G that it's related to and vice versa.
Right.
So what Hume's principle is doing is it's giving us a way of talking about numbers in terms of logic.
Okay. So it's giving us a kind of logical foundation for the concept of number.
Exactly. That's exactly right.
Okay.
Yeah.
Now Frege, he initially thought about using Hume's principle as a definition of number.
Yeah, he did.
But he ran into a problem.
He did. He ran into a famous problem that's now known as the Julius Caesar problem.
Okay. Julius Caesar problem.
Right. And the problem is this.
Yeah.
So Hume's principle tells us when 2 number terms have the same reference.
Okay.
Right? So it tells us when the number of Fs is equal to the number of Gs.
Right.
But it doesn't tell us what numbers are.
Oh, okay.
Right.
It doesn't tell us like whether Julius Caesar is a number.
Right. It doesn't tell us whether, any objects that we might think is not a number is actually a number.
Right.
Yeah.
And it seems like we need some way of distinguishing numbers from other things.
Right. And this is a big problem because if we can't distinguish numbers from other things, then we can't really say that arithmetic is about numbers.
Right. It could be about anything.
Exactly.
Okay. So Frege realizes this is a problem with Hume's principle.
Yeah.
And he ends up going in a different direction.
Right.
He tries to define numbers in terms of classes.
Right.
Or what he calls extensions of concepts.
That's right. Yeah. So the idea is that the number 2, for example, is the extension of the concept equal in number to the concept F.
Okay, so it's the class of all concepts that have two things falling under them.
Right. So the concept of apple in the basket, if there are two apples in the basket, then that concept would fall under the class of concepts that have two things falling under them.
Okay.
Right.
Okay. So he's trying to define numbers as these collections of concepts.
Exactly. Yeah.
Now this leads him to his big work, Grundgesetz der Arithmetik, which is German for basic laws of arithmetic.
Right.
And this is where he really tries to lay out his whole logicist system. And in this work, he introduces this very important principle called basic law V.
Right.
So what is basic law V?
So basic law of V, it's a principle about classes.
Okay.
And it says that two classes are identical if and only if they have the same members.
Right.
So in more formal terms, it says that the class of all x such that phi of x is equal to the class of all x such that psi of x.
Okay.
If and only if for all x, phi of x, if and only if psi of x.
Okay.
Yeah.
So if two classes have the same members, they're the same class.
Exactly.
Okay. And Frege thought that this was a basic logical law.
Yeah.
Right. This was something that was just true in virtue of logic.
Right. And it was crucial to his project.
Okay. Why was it so crucial?
Well, he was trying to unify arithmetic and analysis within a general theory of classes.
Okay.
So he thought that classes were logical objects.
Okay.
And that the principles of arithmetic could be derived from these more basic principles about classes.
Yeah.
And basic law V was one of these basic principles.
Right. So it was like a foundational principle from which he could derive everything else.
Exactly. That's exactly right.
Okay. Now it turns out that basic law V leads to some problems.
It does, yeah.
It leads to what's called naive comprehension.
Right.
And what is naive comprehension?
So naive comprehension is the principle that says that for any property, there exists a set of all and only the things that have that property.
Okay.
So for any predicate that you can come up with, there's a set of all the things that satisfy that predicate.
Okay.
Yeah.
So if I have the predicate is red,
right,
then there's a set of all red things.
Exactly.
Yeah.
And the problem is that basic law V, well, actually, even if Frege had used a free logic,
right,
which is a kind of logic where you don't assume that every term refers to an object,
right,
basic law V would still lead to naive comprehension.
Okay. Why is that?
Because basic law V implies that a class is identical to itself whenever the defining predicate is equivalent to itself.
Okay.
Right.
So if the predicate is just like X is X,
right,
that's always true.
Right, and that's always going to